All righty, let me go ahead and share my screen. And what I'm gonna do today is we're gonna be talking about potential energy. Potential energy. And let me go ahead and define your potential energy, which I'm gonna give it the letter P as, let me go ahead and as the stored energy, which results from precision, from or configuration. Now, when you talk about potential energy, we're talking about joules, which we give it a letter J, which is your unit. Actually, let me get a different color, which is going to be your unit for your potential energy. And what is a joule? Well, we looked at it as before as your Newton meters. And for Newton, and M for meters, which is, let me go ahead and just write this down. Your newtons is going to equal your kilogram meters per second squared. Wonderful. Now, when we have a force acting on an object, or let me just actually go when a force is acting on an object of position only, it is a conservative force. Which means it can be represented as the integral f of x equals minus du over d of x, which we're going to go ahead and answer u as your potential energy. Now, to solve the integral for this form, this means that, and actually, let me go ahead and write that down on the other page. So you got minus du over d of x equals f of x. That means your potential energy, u of x, you take the integral of both sides, is going to be that's f of x times d of x, and it's going to be integral don't forget the negative goes on the other side from beginning to final x initial to x final. Now, notice that we have this negative sign. Now, why is this a negative? Why negative? Now, this negative sign is to show that if the potential energy increases with increasing distance the force will move towards smaller distance to decrease the potential energy. So we can actually, when we actually talk about this, we're talking about your R vector, which is your X, Y, and Z. So we can actually say that the potential energy is going to equal to minus from initial to final, R initial to R final, F dot D of R. So when we actually talk about, let's say we have two objects. Let's say we have an object over here. Let's say this is the ground. And you got an object. This object is in a distance, I would say y, because you're going on the y-axis. Now the potential energy for this object with the mass m is going to be your mass times your gravity times your height, which is 9.8 meters per second square. H is for your. In this case, your F force, and this is going to be in your y direction, is going to be minus du over d of y, which is going to be minus d over d of y for your potential energy that we actually have it as mgh. In this case, our h is going to be in the y direction, which means that this force, F of y, is going to equal minus m of g. Which concludes that the potential energy, and I'm going to go ahead and use U again, your potential energy, which is going to be U, which we said is going to be your negative the integral of your force times d of x. So this one is going to be F of y, d of y is going to equal to minus the integral or minus mg d of y, which is going to equal to mg integral d of y, which is going to equal to mgy. Hence, our potential energy over here is going to equal to mgh, and in our case, is going to be y. All right, now let's take a look at a spring. So, in a case of a spring, let's say this is our spring over here, and this is connected to a ball of mass m. And let me actually come over here, and let's say you go ahead and take this string over here, and let me actually redraw this. This is your mass m over here, where it is moved at a distance, let's call this distance x. Now your force in the x direction, which we actually we said is going to equal to the change in potential energy divided by x, which is going to be minus d over d of x. And in this case, your potential energy is 1/2 k x squared. Actually, let me just go ahead and solve for the potential energy force. So when we talk about the force, we're talking about your minus k of x. K, that's your spring constant. X, that's your distance or displacement that you went in. Having to solve this for your potential energy, which is going to equal to minus f of x, d of x. This is going to equal to your integral from your x initial to your x final minus k of x, d of x, which is going to equal to your potential energy. And let me just go ahead and put this as potential energy, which is going to equal to the negative times the negative becomes a positive. K comes out, you got x. So this is going to become k x d of x, which would be x squared over 2, which is going to equal to 1/2 k of x squared. So in this case, our potential energy is 1/2 kx squared. And again, your force is minus k of x. Again, your negative is on, in this case, is your direction because you're going in the opposite side. That's how much force to go back to restoration force. So basically, your potential energy, down, energy, which we gave it the letter U. For gravitational is going to equal to mgh for your spring. Is going to equal to 1/2 kx squared. I hope you enjoyed this video. Go ahead. If you have any questions, just please email me, abunaemeh@gmail.com. Have a nice day.